Say you got COVID, huh? You don't need to see any of this. All right. So, like I said, I was just telling everybody, the only reaction you guys know that makes a carbon-carbon bond is going to be the alkyne anion doing an SN2 on an alkyl halide. That only works with the alkyne anion. That only works with a primary alkyl halide. All right, you can't do this with secondary. So we do that. If we take our initial 3 carbons from this molecule, you can just take that proton off the terminal alkyne with a strong base. That gives us this anion. We do the SN2 here. We now have a 6 carbon, so we have 2 hexyne. When we do the ozonolysis, that's just going to slice right through the middle of that double bond. We'll get a 2 carbon acid and a 4 carbon acid. But these 3 carbons all end up in the product, so you have to account for them coming from the alkyne. Okay, so now your synthesis basically boils down to this. How do you do that? Okay, so if you haven't done that already, if you figured that out, take a crack at the synthesis on the right. If you haven't, give this a shot now. All right, this now is a simpler synthesis than you had. For the folks watching at home, your last step is going to be an ozonolysis, slice through the triple bond. All right, I'll give you guys another few minutes to work on this last bit. All right. So, I find with these synthesis problems, and I still do this a fair amount. I think I said that the other day. This is a common thing in organic chemistry, and it kind of sets organic chemists apart. Like, why do we have different divisions? The thing that organic chemists do, how far back do I want to go? Like, I said this at the beginning, organic, if you look at the etymology of the word organic, and then you look at the etymology of the word biochemistry and organic chemistry sort of mean the same thing. The thing that really sets organic chemistry apart today is that we tend to build molecules. Right? So if you're a biochemist, you may want to study the effect of some molecule on something. And most of the biochemists are not going to make that molecule. They're going to find it somewhere. Or they're going to collaborate with an organic chemist who makes it. Right? Just like an organic chemist is not typically going to go do really sophisticated biochemical experiments. If I make a molecule in the lab that I think is going to have some interesting biochemical or pharmaceutical property, I'm going to find someone to do those experiments for me. Right? So I actually do a fair amount of this. And if you guys have been able to come to my office much, and you might have seen this on Zoom, I have a whiteboard behind me, and you'll see scribbles like this all the time. So what I would say is, and one reason I don't like to ask these questions on exams is it's a puzzle, right? And the puzzle kind of questions, if you work at puzzles long enough, right, how long did it take you to work that puzzle? Really, probably maybe 30 minutes of actually assembling stuff. But then there's the 4 days you sat there not able to find a piece. And so that sucks on an exam, right? If it's a puzzle that you just don't see the start of it, you're screwed. So what I would recommend, and you can't really do it here in the class, but I'm just saying when you work this problem on the final project, don't think, okay, I'm going to block out 6 hours and I'm just going to suffer through this synthesis. You might be able to do that. Take a look at it, write some stuff down. Do write some stuff down. You should get a whiteboard, get lots of paper, write things down. Give yourself 20 minutes. Whatever you get in 20 minutes, leave it written down, and then just walk away from it, right, and come back to it. And I tend to recommend this for problem solving. And if you want to ask me, then why do I give you timed exams? I don't know. I'm a professor and I live in the U.S. in the 21st century. Actual problem solving, usually you can't just force yourself to do it on a schedule. You can get better at that, and that's why we do give exams. But most of the really hard problems you solve in your life will take coming back to it, leaving, not thinking about it. And you guys have done this already. You know this. So don't think that you have to just push through in one go on that synthesis on the final project. Okay, so here we go. 3 carbon alkyne, we need to do some reactions to get to this bromide. Again, you want to think backwards here. Right? How do you know, what reactions do you know to make a bromide?
HBr.
So you know how to add HBr to alkenes. What else do you know?
Br2.
What's that?
Br2.
You can do Br2 and add, that would add you'd get a bromide you don't need there. The other reaction you actually, and I don't know if you remember, you know this. We talked about this a little bit, and actually I didn't tell you had to know this, so never mind. That reaction is in chapter, can't remember if it's in 7 or not. But there's a reaction with SOCl2 that will turn an OH into a Cl. That would work too, right? I said this is a Br, so if anybody did this with chlorine or iodine, that's fine. All right. Br is going to be the easier one to get to. So you know how to add HBr. So this could go back to an alkene. Now what happens if I add HBr to that alkene? What do I get?
You have it on the more substituted part?
Yeah. So if I do this reaction, I get Markovnikov addition of HBr, I get the wrong bromide. So what do I have to add? You have to add a peroxide. So this is actually going to end up being, so your synthesis here will be, oh wait, I'm not done yet, crap. I didn't take you all through. I'm about to just tell you stuff. All right, so you can get here HBr and peroxide from propene. So how do I get the propene from the alkyne?
H2.
And what catalyst? Yeah. So going backwards, this would be, well, it'd be this alkyne. There's actually two choices here. You can use H2 and Lindlar's, or you can use sodium and ammonia. Right? It doesn't matter on this in this one because there's no stereochemistry. So H2 and Lindlar's gives you the cis alkene. Sodium and ammonia gives you the trans alkene. But since this, you just want to make sure you stop at the alkene. So if I just take the alkyne, I do H2 and palladium, I get the alkane, and then I'm stuck. All right, so let me write this synthesis out. If that's what you write on your exam page, that would give you full credit. All right, so I'm gonna tell you a little bit more about how to answer this. It could be this simple. Of course, so let me say now, you're gonna be doing this final project as an at-home, take-home thing. So if you just like write down this magic answer that comes from nowhere, I'll be suspicious. But if it's right, then I probably don't say anything. But if it's wrong, right, if you get these out of order or you miss one and I see no work, then there's not much partial credit that can come. So honestly, you'd probably want to do an intermediate for each one of these. So H2 and Lindlar's, and then HBr. And now that gives you this one. So like I said, the restriction here that all the carbons come from propyne mean you have to show sort of all of this stuff. So then, again, let's take this. So if I hit the terminal alkyne with a strong base, I get this anion. Then I do an SN2. And that's the step that adds carbons, right? I have to go from a molecule with 3 carbons to a molecule with 4 carbons. So I have to add carbons. Now, I add too many, right? I get 6. So I think a lot of you were probably trying to like add 1 carbon, which is logical. I got to add 1 carbon. I don't want to do it. I don't want to do more work than that. But it's easier if you add more, and especially if you, as you guys work backwards, I don't know how many, I know a lot of you figured out this ozonolysis really quick. And again, the advantage you have, that's the only way right now that you guys know to make a carboxylic acid. All right, so cutting through here, your alkyne's going to be split in half, which means, you know, if you did this, if you did ozonolysis here, you'd get 1 carbon acid and a 2 carbon acid. That doesn't get you where you need to go. So cutting through here, that's how you add. If you think about it, you are adding 1 carbon. You're taking your 3 carbons from the propyne that you've turned down to an alkane, and you're adding the 1 carbon here. You're just adding it in a big group that you then cut in half. And then finally, ozone and H2O. So I would recommend putting all the intermediates in. And I may even say that in the instructions, basically, on your synthesis. It should be clean. If you print this out, don't just start writing lots of doodles all over it. Like, do this on a piece of notebook paper and then write down a clean answer on your sheet. And so what I'll leave you with this. I saw that some of you made some progress on that one. Again, you're going to start with a 2 carbon unit. You're going to end with a molecule that has 6 carbons. I want to reiterate, you can use acetylene here a whole bunch. Right? It's not like I give you 1 molecule of acetylene. This really would. I'd give you a torch. All right, questions? So I will send an email tomorrow with directions on where and, well, not when. The when is established. Your exam will be 12:30 on Tuesday. And it will take 75 minutes, so you'll be done at 1:45. And then, but I'll let you know where it's going to be. And I will either be very available on Monday, or I will have some sort of review session on Sunday. That's all I got. So oh, wait,
Do you
question.
want to talk about iodine?
Do I want? Yeah, I did. I did. When you say that, I'm like, I told her to remind me to talk about iodine. What am I going to talk about iodine? Oh yeah, no, I got it. I got it. Sorry. I was just about to get all emotional and weepy that we're going away, but iodine. I did want to talk about iodine. On the, was it a phenyl? I can't remember. It was something like, it was like this, right? So 1I2 methanol, 2 sodium methoxide. All right, this was from the worksheet that you turned in Monday. And so what I wanted to say about iodine is it does not do this reaction. Okay, so you can't just add 2 iodines to an alkene under most circumstances. And the reason for that is not that nothing happens. A reaction definitely takes place. But the equilibrium is just about 1. Okay, so we get 2 carbon iodide bonds on the right. Carbon iodide bonds are really weak. Right? We break a pi bond, we break an II sigma bond. Those are also weak bonds. Right? A pi bond is not real strong, an iodine bond is not real strong. And it works out that if you factor entropy in, the equilibrium constant for this reaction is going to be 1 plus or minus a bit. All right, so depending on what the alkene is, you're going to have roughly 50% of the diiodide and 50% of the alkene and the iodine, which means it's not a productive reaction. A reaction that overall has an equilibrium constant of 1 is just not useful. Okay. But if you do this with better nucleophile. So if we put something else in there, let's say we put water in, this reaction actually works really well. All right, this is the halohydrin. And now what drives this reaction is you still make one Ci bond, which is weak. But you also make a CO sigma bond, which is really strong. All right, so that does push the equilibrium. So I don't know, a fair number of people on this worksheet sort of did not use iodine. And even like wrote me notes saying, I don't like my mechanism, but I can't, iodine doesn't do this reaction, so I can't think what happens. All right, so yeah, the first step that happens here is the alkene attacks the I. We end up with this iodonium ion, right? And then methanol attacks that, and we end up with an anti-addition, so this is racemic. And then we lose the proton. So that's the other thing I would say here. The most common mistake on this problem was people taking the O-methyl and attacking without the H. So sort of either drawing methanol attacking, but then the H just vanishes, which is wrong, or explicitly saying that it's OCH3 minus that attacks, and you don't have OCH3 minus in here. So you got to turn this into two steps. So the second step, some base is going to take that proton. And then the iodine, going from the iodide to the alkene is just an E2 elimination. But the thing I wanted to say about iodine is it makes the iodonium ion. But if there's not a better nucleophile than iodide around, nothing happens. Right? So you need something that's a better nucleophile than iodide. Thanks, man. All right. So not all weepy, but I've really enjoyed teaching this class. And I mean, we're a long way from done, right? You got like 2 exams left and a final project. Doesn't feel done, but I'll see you guys on Tuesday, probably at some review sessions. The rest of it's going to be online, and I won't see you again until next semester. So anyway, thanks for hanging in there and coming to class. You're like 95% of my human contact. It's you guys and my wife. Congratulations. Anyway, take care of yourselves. Have a good Thanksgiving. Be safe in your travels. Be safe in your behavior. And good luck on all your exams and stuff. Thank you. You bet.